All right. So it's time to start the I²CNER webinar. So good afternoon for the participants in Japan, and good morning for the participants in Europe. Thank you for joining I²CNER seminar series. I am Masanobu Kubota, professor at I²CNER. I'm going to be the chair for the webinar today. I'm very glad to see many audience on the screen. Welcome to I²CNER webinar. We, I²CNER, launched this seminar series in 2010. Since then, we invited many distinguished researchers worldwide. The speaker today is Professor Reiner Kirchheim at the University of Göttingen in Germany. Usually, our director, Professor Petros Sophronis, gives some words before introducing him. But now, US is 2:00 a.m., so he cannot give us the words. So before we begin, I'd like to take a moment to remind you that we will have discussion after presentation. During presentation, please keep unmute. This webinar will be recorded by I²CNER. However, recording by audience and taking screenshots and photos of the presentation are prohibited. Next, I'd like to introduce Professor Reiner Kirchheim. He is one of the PIs of I²CNER. As you can see in the abstract of his presentation, his major research interest is hydrogen embrittlement. Particularly, it related to solute and defect interaction, focusing on hydrogen. I²CNER and the University of Göttingen have established a solid relationship. You may remember a workshop at Göttingen University in 2018. I and Petros have had joint project on hydrogen embrittlement with researchers at Institute of Materialphysik in University of Göttingen. Actually, we jointly published a paper on the fundamental study on crack initiation in January this year. They have very advanced microstructure characterization technique. The paper fully utilizes their advanced observation technique. Professor Reiner Kirchheim is a distinguished professor of Lower Saxony at the University of Göttingen and an external member of the Max Planck Institute for Ion Research in Düsseldorf. He worked at the Max Planck for metals research as a research scientist and senior group leader from 1971 until 1993, and received his PhD in physics from the University of Stuttgart in 1973. From 1993 to 2008, he was the director of the Institute for Material Physics at the University of Göttingen. He is known for his research in thermodynamics and kinetics of materials. In fact, he has established a unique theory of defactant, which is a solute being enriched as a defect based on thermodynamics. He is a member of the Göttingen Academy of Science, the German National Academy of Technical Science, and the US National Academy of Engineering. In addition, he received many big awards, such as Carl Wagner Prize 1990, the Honda Memorial Award 2003, the Hein Memorial Medal 2005, the Lee Chun Lecture Award 2007, the Staudinger Lecture at ETH Zurich, and the Talbot Distinguished Lecture at the University of Illinois at Urbana-Champaign. So, all right, let's move on to his presentation. So, his talk today is about hydrogen affecting defect, density, and mobility in metals and vice versa. So, Professor Kirchheim, please begin your presentation.
Yeah, thank you very much, Professor Kubota, for the very kind introduction. And good afternoon to everybody. Today I will talk about some fundamental aspects of hydrogen. Let me see. Okay, some fundamental aspects of hydrogen, how hydrogen affects the density and the mobility of defects, and vice versa, how the defects or the microstructure in general are changing the mobility and the solubility of hydrogen. And the central role in all that is played by the chemical potential of hydrogen. So for physicists, it's nothing else than the derivative of the free energy with respect to the hydrogen concentration. Chemists like to use activity of hydrogen, which is related via this equation to the chemical potential. And if hydrogen gas externally is provided, then it makes sense to use the pressure of hydrogen as a measure of the chemical potential of hydrogen. Very often people are talking about the lattice concentration of hydrogen, which is related to the chemical potential via the last equation on the right-hand side. But the lattice hydrogen, that means hydrogen sitting on normal lattice sites far away from defects, this is not very well defined. You may define it via thermal desorption, saying that all the hydrogen being desorbed below, let's say, 200 or 300 degrees centigrade is nothing else than the lattice or the diffusible hydrogen. But this is not related to the total hydrogen concentration, as I will show in a few minutes. But it all starts with the absorption of hydrogen, either during production or service. And I will show you that, again, it is the chemical potential which determines the rate of ingress of hydrogen. And then, as Professor Kubota already mentioned, the defect generation and also the motion of these defects, meaning dislocations, grain boundaries, internal surfaces, is also affected by the chemical potential of hydrogen, either being provided internally or externally. And this will be the defactant concept. So I've listed most of the very interesting defects, let's say vacancies, dislocation, grain boundaries, and so on. And I will not talk much about vacancies, also measurements of the high temperature creep by Professor Masanobu Kubota are indicating that vacancies are playing a major role in this context. If you are interested in vacancies, besides the general concept, this is published in a book chapter, Hydrogen Metals in the Physical Metallurgy series. I will also very often call defects discontinuities of the crystal lattice. This is a more positive term, and it has the advantage of including internal surfaces as well. And what I'm going to talk about is is mostly related to hydrogen, but, and this is the nice thing about fundamental aspects, it's also true for other solutes like oxygen or carbon and so on. Now let's start with one example for the ingress of hydrogen. Let's say iron is corroding either in water vapor or in H2S, forming the corresponding oxide or the sulfide. The reaction-free enthalpies are given here, and they are related, according to thermodynamics, to the chemical potential of, let me see if I can get rid of this, to the chemical potential via this equation, and it means the chemical potential of all the participants, and it includes the hydrogen pressure and the pressure of the hydrogen gas, for instance. Now, if you calculate with the given the formulas up here, the ratio of hydrogen pressure to the pressure of H2S or the pressure of H2O, it gives this graph on the right-hand side, meaning that you have very high ratios, very high pressures of hydrogen if it is exposed to H2S. That means, for instance, with water at room temperature, you have about 2 kilopascals of hydrogen of water pressure, and this gives you 20 megapascals of hydrogen according to this equation. But for H2S, it's much more pronounced. It gives you 200 terapascals. Okay, this is simply a figure telling you something about the activity of hydrogen, because which is not included in these reactions, that hydrogen may leave the sample as gaseous hydrogen. Now here's another example, and I was very much intrigued by the measurements of Professor Matsunoga at I²CNER, because he showed that in aluminum alloys, even pressures of 100 megapascals of hydrogen had no effect, or not a very much pronounced effect compared to water vapor. Now you can do the same, write down the equation of aluminum corroding in water vapor, forming aluminum oxide. And this aluminum oxide is a very pronounced oxide former, very high negative energy of formation, and therefore the ratio of hydrogen pressure to the pressure of water vapor is very, very high. So at room temperature, it reaches 10 to the 52. Again, this is just a figure telling us something about the activity of hydrogen. And this is very, very high. And so at a normal 80% humidity you might have right now in Fukuoka, corresponds to 2 times 10 to the 3rd gigapascal pascal of hydrogen, which is 10 to the 55. So very, very high pressure of hydrogen in aluminum alloys reacting with water. Here's another example of protons being implanted in a material that plays a very important role in tungsten in fusion reactors, where you have always protons hitting the walls, and tungsten is considered to be a wall material. So if you set equal the hydrogen chemical potential of dissolved hydrogen to the chemical potential of hydrogen in the gas phase, then you end up finally with Sievert's law. That means that the solubility of hydrogen is proportional to the pressure, to the square root of the pressure of hydrogen. If you plot that for tungsten, for instance, you get again very high pressures of hydrogen, and even at a few atomic ppm of hydrogen, they give pressures much larger than the theoretical shear strength of the material. And that means if you implant higher concentrations than a few atomic ppm, what you observe, and people do so, that blisters on the surface, and they are due to voids being formed internally. And what they did at the Institute for Plasma Research in Germany, in Munich, they drilled a hole with an ion beam and then the whole thing collapsed. So it seems to be a lot of elastic deformation taking place, but looking closer at the crack tips later on in electron microscopy, they see some activity of dislocations. So it's both, it's elastic and plastic deformation. Now, in order to describe the behavior of hydrogen in a given microstructure, that means a given distribution of dislocations and grain boundaries and so on, we developed a concept describing the defects by a so-called energy landscape. That means in a single crystal, hydrogen moving through the single crystal will see a potential trace as here. If you have a vacancy next to the vacancy, the energy is lowered. And if you have a dislocation, let's say an edge dislocation below the Clyde plane, the energy for hydrogen is lowered, and above the Clyde plane it's higher. And for grain boundaries, you have a bimodal distribution. Within the grains, it's like in a single crystal, and in the grain boundary, you have all kinds of different site energies. And you can present that graphically. So physicists will call that a one-level system. This is a two-level system regarding the energy. This is a continuous distribution, and this is the bimodal distribution as shown here. Now, if you add, and this can be described in an analytical form, this energy distribution shown here. And now putting hydrogen into the material, it goes to the low energy sites, and this is determined by Fermi-Dirac function. N is this given energy distribution function. And here, mu is nothing else than the chemical potential of hydrogen. Or in this context, people call it the Fermi energy of hydrogen. Now, if you use these equations here, you end up with the chemical potential of hydrogen, and this is nothing else for the single crystal, the logarithmic form. It's more complicated here. And for the interaction, for the elastic interaction with an edge dislocation, it's described by this equation, depending on the square root of the reciprocal concentration. And I will take this and compare it with measurements we have made regarding the chemical potential of hydrogen in palladium that was deformed palladium, so it contained a lot of dislocations. And you see, if you plot it versus the reciprocal square root of concentration as given by this equation, you get a straight line. And at very low concentrations, which is on the right-hand side, it's no longer elastic interaction, and it is the interaction with the core. So this is a constant energy and a constant chemical potential. But it's not, as this equation suggests, it's not going through the origin, and this is due to HH interaction. So if you apply an HH interaction term here via a quasi-chemical approach, then you can describe this behavior very nicely. And what it means is that at very low concentration, most of the hydrogen is sitting at the edge dislocation. A few amount is in the lattice. And if you increase total concentration, this amount is growing. So it's kind of a cylinder, if you think in 3 dimensions. And increasing it further on, this cylinder grows in diameter, and more of the hydrogen is sitting in normal lattice sites, being diffusible. And in order to check whether this is right or not, we did some small angle Newton scattering, and this gives you directly the diameter or the radius of the cylinders, and you see it increases as a function of concentration. Now, to describe the mobility of hydrogen migrating through this energy landscape in a most general case. But it's very difficult because the settle point energies are also showing a distribution. And in order to make it simple and to end up with an analytical equation, we assumed that we have a constant settle point energy. Then we averaged over all the jump frequencies, assuming thermal activation. And the result is very interesting, that the activation energy is the one between the average and the constant settle point energy. minus the chemical potential of hydrogen. So here it's coming up again, the chemical potential. And that means if you increase concentration, the diffusivity goes up. And simply because if you increase concentration, you have to occupy sites of higher energy, and therefore the Fermi energy or the chemical potential is coming closer to the constant settle point energy, and therefore it increases. So we applied that to palladium containing dislocations, compared it to single crystalline palladium, measuring the diffusion coefficient as a function of the concentration, very low concentration of 1 atomic ppm of hydrogen. And then if concentration increases, to saturate the dislocations, and then finally you approach the value of the single crystalline material. And the blue line is calculated from measured chemical potentials via this equation, no fitting parameter. And as I said before, is a rather very general approach, meaning that everything migrating in a potential energy landscape, like small molecules in polymers, and so every site is different in the polymers due to a random arrangement of these macromolecules. And now, if you measure the diffusion coefficients as a function of concentration, again, the blue lines are calculated. In this case, we need one fitting parameter, but it doesn't change the slope, it doesn't change the curvature. So this is a nice example for the validity of this approach. Now, here is an example for the interaction with palladium, where we applied this concept, measurements of the chemical potential, or expressed here in terms of the partial pressure of hydrogen as a function of the concentration. In a double logarithmic plot for the single crystal, you have a slope of 2 according to Sievert's law. But for the nanocrystalline material and containing lots of grain boundaries, as shown schematically up here, you have a higher concentration. That means the difference is sitting in the grain boundaries, and only a few is sitting within the grains. Now, assuming that for the sites in the grains, you have this one level of energies, and very often people assume that the grain boundaries have all the same segregation energy, but that will be not the case here. What you have to assume is a Gaussian distribution with a certain width of the Gaussian distribution. That means all the sites in the grain boundaries have different segregation energies. So you end up with a dashed line in the plot here, but this is not describing, let me see whether I can use a pointer. No, seems not to be the case. Okay, I can use, okay, if you see my pointer, that's fine here. So in order to explain the deviations occurring at high concentrations, we again assumed H interaction, and then we get the curvature shown here. So measurements of the diffusion coefficients are shown here. For a single crystalline, it does not depend on the concentration. Each of the hydrogen atoms is migrating independently. But for the grain boundaries, we have a lower diffusivity, and this is due to the sites having a lower energy. Hydrogen is kind of trapped in the grain boundaries. And then if you fill up these sites more and more, the concentration increases. And again, you have to take hydrogen-hydrogen interaction into account in order to explain the going down here, the curvature at the high concentrations. It's interesting that different to textbook wisdom, hydrogen is moving slower in grain boundaries at low concentrations, and finally it can take advantage of the open structure of the grain boundary, becoming faster. Now we change gears and are talking about how hydrogen changes the formation of the microstructure. That means the formation of dislocations, grain boundaries, and so on. This is described by the generalized Gibbs adsorption isotherm, which is given here. So the change in surface energy is equal to the coverage of the surface. This is the capital gamma, and A means the solute. And it also depends on the change of the chemical potential of solute A. And I have shown in 207 that this can be applied in a rather general way for all kinds of defects, not only surfaces and grain boundaries, but also dislocations and vacancies. So this is a change of the formation energy of defects or discontinuities, and this is the excess solute at the defect, and this is a chemical potential again. And so we all know surfactants changing the surface energy mainly of water, and this is an abbreviation of surface acting agents. So I use the term defactant as defect acting agents in comparison to the surfactants, and this is a rather general approach to the plastic deformation and how it is affected by solutes. And again, it's not only for hydrogen. Now, here are a few examples how it changes the plastic deformation by hydrogen. So nanoidentation is a well-known technique. What you do is you have an indenter and press the material, and at a certain load, you form dislocation loops. And if you have displacement, the load as a function of the displacement, whenever you form a dislocation loop, you will what people call a pop-in. That means the displacement changes rapidly. And if you use hydrogen, then you see that you get a decrease of the pop-in load, meaning that it is easier to generate dislocation loops in the presence of hydrogen. You can apply the defactant concept and calculate the corresponding stresses here, and then the line energy of the dislocation loop as a function of the hydrogen concentration, which is shown here, and then you got this behavior, and this slope here tells you something about the excess on the dislocation loop, meaning it's about 2 or 3 hydrogen atoms sitting at a distance of 1 nanometer on the dislocation. So it's a reasonable figure. Here's another very simple example for if we cold roll palladium in the presence of hydrogen, different concentrations of hydrogens, and then looking at the microstructure with TEM, then you get these cells with a high dislocation density at the cell walls and no dislocations within the cells. And if you add a little bit of hydrogen, then you get a much higher dislocation density, and the cell size is decreasing. And finally, at 1 atomic percent, you get even a higher dislocation density. And you see a different contrast. That means the orientation of the adjacent cells has changed. So this is now a kind of nanocrystalline material with small angular grain boundaries. And we all know from the work of Ian Robertson that at the crack tip, if you do specific site TEM observations, that with no hydrogen you have some dislocations because the crack propagates by plastic deformation, but with hydrogen you see a higher density of dislocations. So we did an experiment with vanadium, BCC material as well. You form these pillars with a focused ion beam, and if you compress these pillars, you get these shear bands here, very heavy deformation occurring at one shear band mainly. And in the presence of hydrogen, this case 3 atomic percent of hydrogen in vanadium, you see a uniform distribution. You may see some Clyde planes here, but it's many of these shear bands are activated. So again, it means that it's easier to generate dislocations in the presence of hydrogen. Now, I worked together with Petros and Brian Summerday on the very well-known concept of John Hirth and Jim Rice on how hydrogen affects decohesion. And I was lucky to get some results of Christmas and Ethel, the Nobel Prize winner in chemistry. And they measured the excess or the coverage of surfaces of nickels of different orientation as a function of the partial pressure of hydrogen. Also, they used Langmuir isotherm to explain the low concentration behavior. I used the Fromkin isotherm, taking again hydrogen-hydrogen interaction into account, and then I was able to fit these equations. So what I have now is a chemical potential as a function of the coverage. The excess is a function of the chemical potential. So I can use now the defactant concept, saying how much the energy changes as a function of the chemical potential of hydrogen. And then I get this graph. So you see the surfaces are quickly filled with hydrogen at very low pressures of hydrogen, whereas at grain boundaries, it takes a much longer time to fill them. And taking the Gibbs adsorption isotherm to see the change of the surface energy and the change of the grain boundary energy. Now, if you apply the Hirth and Rice model, the work of fracture is 2 times the surface energy, because you form 2 surfaces by opening up a void or a crack, and you gain energy from the grain boundary. And if you use this for the different orientations of the nickel, you see this behavior of the work of the ideal work of fracture as a function of the fugacity of hydrogen or the pressure of hydrogen, and the pressure is given up here. And you see that at the 111, the dense packed plane, it starts at a lower surface energy. It has a higher number of sites for hydrogen, therefore the slope is steeper here. And it reaches zero surface or zero fracture energy at a pressure of 100 megapascal for nickel 111. So again, the defactant concept is helpful in this context to calculate the ideal work of fracture. Now, we are talking about the propagation because one of the arguments people had concerning the John Hirth and Rice model, whether the hydrogen is fast enough to reach the crack tip in order to saturate the surface sites. And you can calculate that in a simple model, assuming that the crack propagates by dA, and then the hydrogen is provided from a cylinder around the crack tip with the diffusion length, which is the diffusivity times 2T. And now these have to be equal. That means the amount of solute delivered has to be the amount of solute sitting on the new formed surfaces, or the crack velocity has to be slower than this term. And in order to show or to get some figures, this is well known, the diffusivity of hydrogen in iron. And if you assume the lattice diffusivity only, or lattice hydrogen being responsible for that, and a coverage of 1 monolayer of hydrogen, this corresponds to a crack velocity of 10 micrometers per second. So a rather slow crack propagation, because the hydrogen has to be provided here. Now, what we did is we measured the formation of internal cracks by heavy cathodic charging. So the dark area is showing the area where hydrogen is provided cathodically, and you see a lot of blisters being formed, and in a cross section you see the cracks near the surface forming these blisters and cracks inside the material. And now if you break up the sample, and the advantage, if you break it, the crack runs along these internal cracks. So you open up the crack surfaces, and looking closer at the initial sites of crack formation, we always see a particle. Also, this was a very pure iron, the purest iron we could get, only containing a few ppm of these substitutional solutions. And now if we do an analysis of this inclusions here, or these precipitates, we see that it is a manganese oxide mainly, and outside we don't see any manganese. We just see the iron peaks. Now this is indication of that this is another example. All these cracks, or at least all we have looked at, contain a precipitate in the middle of the cracks. Now, so far we have shown that the defactant concept is helpful in understanding how defects or discontinuities are generated. Now I will present some examples showing that hydrogen also affects the mobility of the defects. So general wisdom, that means in what is written in textbooks, is that a solute, we have shown this energy landscapes before for an edge dislocation, you have the sites below the glide plane, they are filled with hydrogen, and if you look in this direction, then you have a potential tracer like this. Hydrogen is sitting in here, and if you move the dislocation and hydrogen is immobile, or a solute is immobile, then you have to move them to to sites of higher energy, and this requires energy, and this is slowing down the motion. And Cottrell and Alfred Seeger have shown that this is important for the solute drag effect. And the same, and again, the axis can be determined by the Fermi-Dirac statistics. And if you look at grain boundaries, it's the same. Hydrogen is sitting in these lower energies of the grain boundary. And if you move the grain boundary, you have to replace or put the solutes at sites of higher energy. And this is nothing else than the solute track. Again, that means whenever you have segregation to these extended defects, then their mobility is slowing down. Okay, now, if you look at the movement of a dislocation, and this is now a three-dimensional presentation of an edge dislocation. So you have a line that's shown here at 2 pinning points. And if you move it, it doesn't move as a whole, because nature doesn't like cooperative motion. So it's forming kink pairs in order to move further on. And the motion of these kink pairs is important for, or is the atomic mechanism of the formation or the movement of a dislocation. The same is true for grain boundaries. The atomistic description requires the formation of these lattices, or as people call that, disclinations on the grain boundary surface. And this is shown here in this context. And these move around. They may extend and they move around, and then they hit a triple line, as maybe here at this place. And then it's decided whether energy is gained or not, whether this is extending or stable or not. And this way, grain growth happens. And if we explain that in terms of defects, and what I haven't mentioned to say is that these kinks and these latches I will call secondary discontinuities or secondary defects. Now, if these generation requires energy as well, it means that the defactant concept can be applied here, and meaning that whenever you have segregation to these secondary defects, it's easier to generate them. It means it's easier to move them. Now, that it's not only that the excess, which is determined by the chemical potential, retards motion, that is a solute drag effect, it also enhances the motion of the defects. And again, this is described by the defactant concept. Now, if you look at a dislocation at two pinning points, due to the crystal orientation, you have this step-like behavior. So you form what people call necessary kinks, geometrically necessary kinks. If you apply a small stress, then they all move to the left or to the right, depending on the sign of the stress. And this is nothing else than anelastic deformation. So it's going back and forth. You can determine that by internal friction, as shown in the second transparency. But if time proceeds, you have to form new kink pairs, and that means you bow out this dislocation, and this is nothing else than plastic deformation. And now, in the presence of hydrogen, it's easier to generate these new kinks, and therefore you form more of the kinks, and therefore the dislocation bows out further on, and this means more plastic deformation. And this is it's shown here. So this is a kind of softening happening to hydrogen. And this can be observed by internal friction, this inelastic motion, and without any hydrogen. Again, this is for niobium, a BCC metal, like vanadium, like ferritic steels or iron at low temperatures. And you have these two peaks, and this gamma peak around room temperature is due to the motion of screw dislocations. Now, if you add oxygen, you got a so-called cold work peak or Snow-Custer peak at much higher temperature. So the kinks have to carry along the heavy oxygen, and that's why you need higher temperatures to move the dislocation of the kinks. But with hydrogen, it's the other way around. The Snow-Custer peak or the cold work peak appears at lower temperatures, and this was causing some discussion between two heroes of the dislocation theory, Alfred Seeger and John Hurst. And Seeger, who developed the theory, explained that hydrogen is difficult and we need some theoretical adjustment to explain that. But John Hurst already had the right idea and was suggesting that hydrogen adsorption to the core of the screw dislocation makes double kink or kink pair formation easier. And now we can explain that. Okay, we can explain that in terms of the defactant. So it's no longer a suggestion, it has a thermodynamic basis that it is really easier to generate these dislocations or the kink pairs. Now, this May Martin being in Göttingen for some time, getting a Humboldt award, we did some measurements of grain growth, so the effect hydrogen has on the movement of grain boundaries. So we prepared some thin films of vanadium. So we get a nanocrystalline microstructure to begin with, and then we annealed it in vacuum at 600 and 700 degrees, and in between these two temperatures, we observe grain growth. Now the idea was, which is happening in with other solutes, let's say carbon in iron, for instance, that the grain boundary is decreasing the grain boundary energy. Oh, no, sorry, this hydrogen is decreasing the grain boundary energy, and therefore it is decreasing the driving force for grain growth. So we would have expected that hydrogen is decreasing grain growth. But the other extreme happened, that hydrogen is actually enhancing grain growth. So at very low pressures of hydrogen, 1 Pascal of hydrogen, you see already a remarkable increase of grain growth. And the explanation is again that we affect the secondary discontinuities or secondary defects that leads to the formation of these disclination or lattices. That is easy. And if you look in textbooks, grain growth is determined by the product of mobility and driving force. So we expected in the first place that the driving force being reduced plays the important role, therefore grain growth is reduced, but we haven't considered the mobility. And the mobility, or the increase in mobility due to these formations of secondary defects, is the most important factor in this context or in this experiment, and that's why we got a very much enhanced effect on grain growth. And very recent paper is showing by computer simulations that the same is happening in tungsten. Again, this plays a role in fusion in the wall material of fusion reactors. And again, so it is the same story as with dislocations. Solutes, and in this case, examples I've shown, hydrogen, will accelerate the motion, or in some cases, it will retard the motion. And here's a final example. And again, I was always telling you that's not only hydrogen, where the theoretical concepts I had presented today are valid, but other interstitials as well. And it's well known for a very long time that oxygen in niobium causes at low concentration a softening. So the shear stress for deformation is going down if you increase the oxygen concentration. Very low concentrations, 0.1 atomic percent here, and then it's going up again. And the same is true for nitrogen in iron, measured in Stuttgart by Diel and co-workers. And the flow stress is going down dramatically from 70 to 40, and then it's going up again. And very old measurements of Sato, Meshi, and Quesnel are showing around a temperature of 200 K. We also have softening of iron by adding carbons, and these were atomic ppm at very low concentrations. Though the same is true for all these BCC metals. They show softening at temperatures around 200 K, the same here at 200 K. And the interesting part is that you can explain that because the rate control, if the rate control is determined by the formation of king pairs, then you understand in terms of the defactant concept that you will have a softening. It's easier to generate dislocations. Why it is happening mostly in BCC metals, or it's very much pronounced, this softening in BCC metals, it's due to the fact that in BCC metals, the screw dislocations are determining the plasticity or the deformation, plastic deformation. And if you form kinks at screw dislocations, these kinks have edge type character, and edge dislocations have a much stronger effect on segregation of these interstitials, carbon, nitrogen, and oxygen. That's why it is more pronounced in BCC metals. So I'm at the end of my talk, and thank you for your attention. And I think that I have shown that the defactant concept is very helpful in explaining plastic deformation in the presence of solutes. So thank you again.
Thank you very much, Professor Kirchheim. It's very interesting talk. So now let's open discussions. If you have a question or a comment, please raise your hand. Please make comment, please. Arno, please.
Thank you. Can you hear me?
Yes.
Yes, yes, I do.
Thank you very much, Professor Kirchheim. I always enjoy your talks. I have a question that's close to what you just talked about, and most likely it's about the effect of hydrogen itself and the connection to temperature. Like you just said at the end, that you have the pronounced effect in interstitials at about 200 Kelvin. And I remember a paper by Samantha Lawrence on nickel, where they formed the nickel at, I think, low liquid nitrogen temperature, and they still had some kind of effect of hydrogen. But their discussion was that it should not be able to diffuse at that temperature. So they were discussing about how come there is hydrogen effect, even though the hydrogen is supposedly immobile. And I was wondering if you have, let's say, theories or ideas about the effect of hydrogen being immobile and still having an effect on the mechanical properties in metals.
Okay, that is a very good question, because I was asking myself very often this question. And it's the same for these heavy interstitials. They are immobile, right? Mm-hmm. At 200 K. And at liquid nitrogen, hydrogen is immobile in most metals as well. But you form these dislocations, and they are moving through the material, and they are picking up the solutes. Also, the solute is immobile. The dislocations are moving, and they are picking up the hydrogen. And at the places where the solute is sitting, let's say hydrogen or oxygen, at these places, it's easier to generate kink pairs. So it's not the mobile hydrogen. And in addition, you may argue that along the dislocation line and the core of the dislocation, it might be easier to move the solute, and explaining or using the defactant concept. But it's simply the solute a dislocation has picked up before or during its motion. At these places where the solute is sitting, changing the whole local stresses, it's easier to generate a dislocation, the kink pairs. So thermodynamics doesn't tell you anything about the mechanism, the atomistic mechanism. It simply tells you if it requires energy to generate the kink pairs, then in the presence of solutes, it's easier, right? So if you want to understand that in in an atomistic or atomistic concept, then you have to worry about local stresses and so on. And actually, I think I haven't mentioned that, but some theoreticians in Tsukuba calculating by computers DFT calculations the formation energy of kink pairs in iron, and they showed that for screw dislocations in the presence of hydrogen, it's easier to generate the kink pairs. So it's not only the thermodynamic argument I'm providing, but it's also by DFT calculations made later on proving this concept.
I see. Thank you. Yeah, because actually not only the work with Samantha Lawrence, Dr. Lawrence, but I personally did similar stuff. Like you did a bit with the Palladium, I think, with cold rolling, and I did with iron, with liquid nitrogen. And I was very surprised that there was a higher dislocation density in cold worked iron that was previously charged with hydrogen. And I could not make sense of it because
that was made at room temperature, cold rolling at room temperature by about 50% cross-section reduction.
Mm-hmm. Okay.
And later on, we removed the hydrogen, or it's removed by desorption anyway, before we prepare the thin foils for the TAM observation.
Oh, yes.
But you see, it's dramatic increase in dislocation density.
Yeah, it's that's the thing, because it reminded me of I think there was Professor Delafosse who was talking about how maybe hydrogen does not diffuse along dislocations, but more it's as the dislocation stop after a jump, the hydrogen around it goes to the dislocation. Like aging, I think he was talking about aging. Anyway, thank you very much for the answer. It's given me a lot of food for thought. And thank you very much for the presentation.
You're welcome.
Thank you, Arno. So are there any questions? So I have one question about, you showed nanopillar indentation. So
yeah,
this one, you say the deformation under the effect of in the presence of hydrogen occurs uniformly, but you know, Petros say hydrogen makes the deformation localize the deformation. So I feel this result is opposite. Do you have any comment on this discrepancy?
Yeah, you're right, but this is not crack propagation. So this is deformation along shear bands.
Yes.
And I think Afros Barnos in Norway has shown similar results for iron. And the nice thing about vanadium is that you have a natural oxide, and therefore hydrogen is not able to leave the sample, and which is always a problem. That's why we did nanoidentation with vanadium again, charging it before with hydrogen in a well-defined way, and then did the nanoidentation. Here it is. Maybe you don't see that, but there are many shear bands being formed if you look at higher magnifications at these with hydrogen, at these pillars with hydrogen, and that means it's simply easier because you have so many of the shear bands. Therefore, you have a more homogeneous deformation compared to the case without any hydrogen.
In this experiment, observation of dislocation is possible or not? You know, if we are TEM, can be applied to this experiment?
Yeah, we haven't done that. We could have looked at the dislocation density inside the material, taken by site-specific preparation with the focused ion beam. We could have prepared foils through the pillars and look at the dislocation densities. We haven't done that.
Okay, thank you very much. Okay.
You're welcome.
So does anybody have any questions? I have another question. You showed the heavy cathodic charging for pure iron. You found inclusion or precipitate at the crack origin. So I'd like to ask you about the role of the inclusion. Is it simply a stress concentration or so enrichment of hydrogen concentration?
Yeah, I think I have not mentioned that, but first of all, this reminded me of the work Professor Murakami did at your place. And very often he also was blaming the inclusions of the precipitates to be the initial sites of crack formation. And I think this has something to do with the segregation at the interface between oxides and the ferritic steel and or carbon and or hydrogen and so on. And due to this segregation, these are interstitials. Segregating on the interface means they build up stresses around the interface. And therefore, it's easy to generate a crack due to these stresses. But they want to expand the lattice, but they are forced by the surrounding matrix to do so. And but if you form a crack, then you can release the stresses due to this segregation of solutes. And it's interesting that this depends on the coverage or the composition of the precipitates. And recently, Professor Dr. Takahashi at Nippon Steel, he made some very interesting atom probe analysis of carbides, vanadium carbides. And depending on the stage of annealing, you have segregation of hydrogen or not. And whenever you have no carbon atoms at the interface, you have a very pronounced trapping of hydrogen. And that is due to the vanadium being there present, has a very strong interaction with hydrogen. And again, whenever you have segregation, you build up these stresses, and then it's easier to form cracks. And it's interesting because we didn't expect that. And fortunately, May Martin was, she did together these measurements in Göttingen with Maria Tiegel. And they were brave enough to look very close at these cracks and therefore seeing these precipitates. And it's a high purity iron, so we didn't expect that either.
Okay, thank you. And the last question. I have much interested in the experiment by May Martin. You showed the recrystallization is enhanced by hydrogen.
You mean we were talking about the grain growth of vanadium, or?
Yes, grain growth of vanadium.
Yeah.
So
yeah, that is something you probably will not observe during deformation, because grain growth induced by plastic deformation.
This is a
I think
static.
it's
not
there are maybe a few cases where this happening, but during recrystallization or recovery, this may very well happen. And as grain boundaries play a very important role during the deformation, this will be important, of course, as well.
Yeah. I am thinking the relation between this kind of hydrogen effect and reduced creep life in hydrogen. So recrystallization is one of the major mechanism of the softening at high temperature. The hydrogen enhance the recrystallization. It may affect creep deformation behavior.
Right, that may very well be. And again, the thermodynamic concept doesn't tell us what is a rate determining step. But besides the grain boundaries, the vacancies, as we just talked, play an important role in terms of getting the dislocations away from the pinning points. You need very often you need dislocations, you need vacancies in order to cut other forest dislocations and so on. And then the vacancies play a role. But in creep as well, creep is a rather general term. It may be affected by the grain size, or it may be affected by vacancy concentration and so on, depending on temperature, stress, state, and so on. And but anyway, in any cases, it may help you to get an explanation for the effects you observe.
Probably we have a lot of things to do together about the creep in hydrogen.
That's right, yeah.
Okay, good. Thank you very much.
You're welcome.
Yeah. So the audience, do you have any questions? Okay. Russia, Yomi, please.
Hello, thanks for nice talk. I want to ask about something in slide number 23.
Yeah.
So here the softening happens around a certain range of temperature and then increased. So why it increased after that drop?
Okay, after the softening you get hardening by the solute, and this is simply due to the solute drag effect, because in this range of concentration or temperature, the kink pairs have to carry along the solute, the carbon in this case, or the nitrogen or the oxygen, and this way you need higher stresses to move the dislocations, because the kinks have to carry along the heavy dislocation.
Okay, thank you very much.
Okay, is there any question? It's almost time to close this webinar. Okay. So, okay, so we will close this webinar. So thank you very much again, Professor Kirchheim.
It's my pleasure.
So let's keep in touch and continue the research on creeping hydrogen.
Yeah, okay. Yeah.
Okay, good.
We do so.
Yeah. So thank you very much.
You're welcome. Thank you.
So goodbye.
Bye.
Bye.